For those of you that are new to this, as you know, this is a talk series about WASH, water sanitation, hygiene research happening in Canada or by Canadian-based researchers. And the aim of this is, in the long run, we want to form a maple-themed community of practice around this. And there's a lot of stuff, a lot of good work being done. And this is a bit like a open mic in which we want to showcase different kinds of research done by a variety of people. I have to also say a big thank you to our sponsors. So this is sponsored by UVic's Strategic Impact Fund under our Water Sustainability Collective grant. And I'm even more glad to announce today that maybe some of you have seen on Twitter, but the WASH Canada will be receiving even more support from NSERC. So NSERC, for those of you dialing in from abroad, is our National Natural Science and Engineering Research Council. That's the main source of research funding we have. And I'll do a quick sharing of my screen on what that is. So we have a grant under NSERC that's called the WASH Canada NSERC Create for water and sanitation for low resource contexts. We have a website where you can look up more information, but I'll do a quick overview of what this is. So basically, this is a grant that will provide a unique Canadian training opportunities. And we want to address both domestic and global challenges around safe and sustainable water and sanitation services. So essentially, it's a training program mainly for graduate students. We will fund some undergraduates and some postdoctoral fellows, but mainly masters and PhDs. And really what this funds is we have about 1.65 million over 6 years, and we want to spend it mainly on stipends. So we're going to be supporting students through scholarships that will be trained approximately 40 trainees spread across 8 universities that are enrolled in this program. So this program is being led by University of Victoria, and we have a few of us here. Myself, Heather Buckley, Christian Dabrowski, Tom Gleason, colleagues at UBC, like Sarah Beck, a bit further, SFU, Simon Fraser University is Jane Fowler. And moving on to Ontario, at Guelph, we have Ed McBean, who has spoken in our series before. University of Toronto, David Meyer. Carleton is Anita Basu. And at Western, we have Claire Robinson. And finally, Peter Van Holigen at Université Laval. So that's my brief spiel. I will stop here and hand it over to Kelsey.
Yes, hi everyone. I will be fairly brief, but maybe since this is the beginning of our fall WASH talks, just introduce myself a little bit. So my name is Kelsey. I am a current PhD student at the University of Victoria with the Public Health and Environmental Engineering group, and one of the students in that lab that Caetano heads. And I also spent some time in Switzerland with a research group there looking at decentralized sanitation systems. And so my research, as well as all of the research in our group, is very much related to WASH, and I think it's great to have a spotlight on Canadian WASH. So without further ado, I would also like to introduce our speaker for today, but before I do so, I do just want to acknowledge that currently, I know we're all kind of coming from different parts. One of the great things about keeping these online and accessible, but currently the University of Victoria, just a brief territory acknowledgement, is located on the Saanich territory, and we just want to acknowledge that, and hopefully if you are not in the Victoria area, just take some time to think about where it is that you're coming from today. So without further ado, I would like to introduce our speaker, Professor Karl Linden. He is a professor at the University of Colorado Boulder and an associate director for the Mortensen Center in Global Engineering. And currently he is also a Fulbright Canada Research Chair and actually on sabbatical, where he'll be spending a lot of his time in Canada. So you may be thinking, hey, this guy's coming from a university not in Canada, but he will be spending a lot of his time for his sabbatical here in Canada as well, doing some really great research. And he'll be talking today about UV disinfection for small and distributed systems. So Karl, I'll hand it over to you.
Awesome. Can you see my screen okay? Great. Thanks a lot, Kelsey and Katana. I really appreciate the opportunity to speak with everyone today. And this is a really awesome group. I was really happy to see it created and see, the community around WASH in Canada, having some nice cohesion and direction under Katana's leadership. As Kelsey mentioned, I'm a professor at the University of Colorado, and I'm currently on sabbatical, which is a nice thing for professors. And I am spending time in Halifax, working with folks at Dalhousie and St. Mary's University. And that's funded by Fulbright Canada, which is a great program to bring US academics and students as well to Canada to work on some common problems across borders, and also just to have a cultural exchange and get to know folks and develop new collaborations. So this is really helpful for me. I'm looking forward to visiting folks at UVic. I'm also be visiting UBC as well. I'm planning to visit U of T and École Polytechnique as well. So I'm hoping to get around quite a bit in Canada this fall as part of the fellowship that I have. So it's awesome to speak here, kind of just starting out in the last few weeks on this Fulbright Canada research chair. I was up in Ottawa actually, and up at Carleton, visiting a former postdoc of mine, Banu Ormechi, who's many of you may know. And it's great to see a number of folks who I know as well on the call. So on the webinar today. So hello to everybody, and hello to folks that I don't yet know. As Kelsey mentioned, I'll be talking today about some of our kind of visions and research around bringing UV-based technology kind of outside of the treatment plant, outside of the conventional large treatment plants, and where else can UV be a good solution for mainly for thinking about water disinfection in this case, and it's in distributed systems and pipe networks and in small systems around the world. So let's see, great. So overview of my presentation today. I'll first kind of lay out a vision we put together a couple of years ago and kind of served as a roadmap for a lot of the research we're doing in my group, looking at UV applications both in distribution networks and in small water systems. And I'll frame that by looking at the current state of water distribution issues that are germane to the United States and Canada, but certainly all over the world, concerns with infrastructure. I'll kind of pose a couple of questions about microbial compliance and why is it that in our advanced systems we still have problems, especially in small systems. And then get into some UV-based science and engineering. For those of you who don't know, give some basics on how UV works. What are some of the drivers for UV applications, especially UV LEDs, which is a emerging UV technology that's gotten a lot of interest and really enables a lot of new applications. And talk about some novel applications that I vision and we're doing research on for distribution system treatment, as well as small systems, remote systems for small water treatment. And then thinking about overall, around the world, how we can bring this kind of technology and hopefully help protect public health. So if you look at, let me see if I can get a laser pointer here. Hopefully you can see my laser pointer. Really laying out our vision. We know UV works and has been applied in systems around the world, really, in drinking water and wastewater treatment. Some of the largest municipal systems in the world use UV light for disinfection. It's a very effective technology. It's great for inactivation of all types of pathogens. But thinking about UV applications, there's so many great attributes of UV that why aren't we thinking about it in other places? So we kind of think about bringing UV outside the treatment plant, maybe as waters is transmitted through large transmission mains. Is there a way to add UV as a booster in systems with large pipe networks? Is there a way to put UV in storage tanks? This is usually parts of distribution networks that often get ignored, but often have microbial compliance issues, especially around Legionella and other opportunistic pathogens. And getting further into the system, looking in buildings, certainly point of entry, point of use, UV's got lots of potential applications and actually is used quite a bit for folks who have like cottages up in cottage country, which I'm learning about here in Canada. Certainly UV is used in a lot of those systems that take water from lakes to protect microbial, to protect the water in the household. At the point of use in the faucet or in say a water cooler, UV is already used in those applications. How can we bring UV more into the public as well? And then as we get deeper into the distribution system, is there a way with UV LED technology maybe to bring UV light into distribution systems and smaller pipe networks and help minimize biofilm formation in buildings and other distribution branches, and thinking about control of opportunistic pathogens in those cases as well. We laid this all out in a kind of think piece a couple of years ago in Accounts of Chemical Research. My co-author, I'll introduce a little later, Natalie Hull and Vanessa Spite, help with this vision. So what is the current state of water distribution? We know that this is kind of the last opportunity to protect public health, and thinking about water. Oftentimes the compliance point is as it's entering the distribution system, and what happens in the distribution system, could be a challenge as far as degrading water quality. We know that aging of pipes and deterioration of infrastructure can contribute to problems, whether it's chemical based or microbial based. And then we also know that as the chlorine residual, which in most water systems in North America are required to have a chlorine residual, as that residual decays, there's opportunities for pathogens to form and grow in biofilms. And we also have the concern with chlorination of the formation of DBPs, or disinfection byproducts. So that's also another kind of concern because we use chlorine. In the US, about 94% of the population receive water with a secondary disinfectant. A lot of small systems aren't required if they're small enough. But in many countries around the world, especially some European countries, there's water distribution systems that actually don't use secondary disinfection. This includes systems in the Netherlands, Germany, and Switzerland. And when you look at those systems, they're operating fine. People are not getting sick all the time. Certainly they do water treatment a little bit differently than we tend to do in North America. They're more biological focused, perhaps. We're using biological filtration maybe, or granular activated carbon, whereas we tend to shy away from those things. But certainly it's a fact that many countries don't use any secondary disinfectant, but we're required to in Canada and in the US. So certainly the precedent for not using a secondary disinfectant, a chemical disinfectant, has already been set. But we have all these problems, and is there a way we can maybe think about other alternatives? Is chlorine really the solution and the end of our solution set, to help protect public health as water moves through the treatment plant into the distribution system? Certainly, I think we can do better, and we can have safer water. And as far as distribution systems goes, some of our goals are to, control pathogens for sure. We want to minimize intrusion events. We want to, avoid low pressure events where water might get into the system that's contaminated. Certainly, we don't have any cross connections. We're concerned about metals. Lead is a huge issue in many systems. And obviously DBPs, whether that's from chlorination, we can think about NDMA even as a DBP, but certainly the regulated and unregulated chlorinated disinfection byproducts. We know all of these issues are also driven by the microbiology in the system, and certainly chlorine and chlorination puts pressure on the microbial communities that are able to thrive in water. And that could also be contributing to some of the problems that we have through that selective pressure. If we look at the rates of microbial compliance, in other words, the number of violations, say in total coliform in this case, this is the relative rate of noncompliance. If we set the rate of noncompliance at the Netherlands rate, and we set it all equal to the Netherlands and call that 1, it turns out that the UK Remember, the Netherlands doesn't use a chlorine residual, but in the United Kingdom, which does use a chlorine residual, about 3 to 4 times higher rate of non-compliance. I mean, they have more problems, more regulatory compliance issues than the Netherlands, about 3 to 4 times. And the United States, has over 15, almost 20 times the rate of non-compliance for total call form violations. And so you ask the question, well, I thought chlorine is supposed to protect us, against microbial issues in the distribution system. But in the cases of the Netherlands, there's no residual for chlorination. In the UK and the US, there is a chlorine residual applied, yet we have these challenges of non-compliance that are higher than other countries that actually don't even use chlorine. So this brings a lot of questions in my mind, and something I've been thinking about since working on UV technologies. And when you look at small systems, we haven't had bigger challenges. And this graph shows populations of serving the water systems that serve populations less than 10,000 people here on the left, and the water systems that serve populations greater than 10,000. So you see the numbers here. We have the number of systems serving less than 10,000 people. We have almost 150,000 systems that serve small communities, and larger systems have a lot fewer, but they serve a lot more people. Over 250 million people are served by large systems. This is all data for the US from the EPA back in 2017. We have about 50 to 60 million people served in small systems. When we look at the violations, the number of violations that occur, the number of violations in large systems are much, much lower compared to small systems. And among those total violations, the number related to health specifically are very, very concerning in small systems. We have 40,000 violations related to health concerns, meaning like there's coliform violations, there's chemical violations. So these are things, not just system-based violations, say, we're missing a residual or something, but they're actual health-based violations. And so small systems are much more vulnerable to violations than large systems, and yet they're often ignored, and we don't often think about designing technology and solutions around small system applications. So what is the problem here? I mean, we have certainly aging distribution systems, which I mentioned before. We have issues with decaying disinfectants, water stagnation. All these things add to problems in small systems. We have microbial growth in forms of biofilms, and especially concerning with opportunistic pathogens, things like Legionella or Pseudomonas, that can get into our pipe networks and contaminate water, especially in buildings and premise plumbing. In all systems, they have maintenance and upkeep issues, especially in small systems, because we don't have a lot of trained personnel to work on those systems and maintain them. And also the technologies we use can be burdensome on the operators. And we certainly have a lack of interventions to solve the problems. We have these problems, they're still persisting. And in this day and age, it's just not acceptable given the types of technologies that we have. So you got to ask the question, is there a way for other improvements we can make? And for me, working in the area of UV technology, it's always been, a vision of mine to have UV technology be part of the solution, because it can deliver safe water and doesn't leave a concerning residual or create byproducts. So this could be an interesting opportunity here. So UV itself is a technology, it's a physical-based technology. It acts to disrupt the replication of an organism's genome, and the light actually gets absorbed by specific biomolecules that destroy its ability to replicate. And so the light just comes in, it doesn't use any chemicals, and it effectively inactivates anything with nucleic acids, which is all types of life, obviously, at certain wavelengths. It's quite effective. And these wavelengths tend to be in what we call the UVC range, which ranges from about 200 nanometers up to 280 nanometers. And this range here overlaps really nicely with the peak absorbance of the genomic material, the DNA and RNA in an organism. So we get absorption of those biomolecules by UV light. That energy from the photons goes in and breaks up the bonds, destroys the bonds, and creates DNA damage sites, like here in this cartoon, before and after, showing the damage to the double-strand DNA. This is how UV works. It works the same way in all organisms. Everything has nucleic acids. Sometimes viruses have maybe single-stranded RNA or DNA, but that works just as well. And It works against protozoa, which tend to be more resistant to things like chlorination. So Cryptosporidium and Giardia are equally affected by UV light, as are bacteria. We look at the mechanisms of how UV works. There's both genome damage, as I mentioned before, but there's also protein damage. In this graph here, I have wavelengths between, say, 220 nanometers up to about 320 nanometers. Remember that UVC range is right in here, say 200 to 280. And when you look at the absorption of proteins, it's just a general protein absorption, a mixture of various proteins, and you look at the absorption of DNA here, basically representing nucleic acids, you can see different features and different parts of the spectrum that absorb better than others. Now, if we look at the genome damage, we have specific absorption here between, say, about 240 to 280 nanometers, very high absorption, which means that these photons are going to get highly absorbed, which means they're going to transfer the energy and break those bonds at these wavelengths, as well as below 220 nanometers is quite high as well. If we look at protein damage, those wavelengths tend to be a little bit higher, and this hump here around 280 nanometers is well absorbed. But we really find proteins are highly absorbed at very low wavelengths. And especially for viruses, this is really important because viruses use proteins as part of their infection cycle. So their proteins on the fiber proteins or proteins on the outer parts of the virus can act to actually find the host cells. And if we can damage those proteins, the virus won't be able to find our host cells, won't be able to cause an infection in the first place. So protein damage tends to be very important for virus inactivation. And we find these low wavelengths are very, very effective for viruses. In fact, sometimes up to 10 times higher than the typical UV at 254 nanometers, which is used for most disinfection applications. So low wavelengths are also really interesting to use in a big research area and a number of research groups. There's many types of UV devices that you can use. The most conventional UV source is this low pressure mercury lamp shown here in this black line. That has a really nice, unique single emission at 253.7 nanometers, we said 254. And that's basically the only wavelength that is emitted from this lamp. And it's a typical, in the UV range, and it's a typical fluorescent lamp you might find in an office. These are exactly the same construction, except they don't have that white phosphor coating on them. They're just clear quartz. And the UV light generated in those mercury lamps is purely at 254. And that's very effective for inactivation. For DNA damage. But there's other UV sources that are really exciting too, especially the LEDs. LEDs are really ready for use already. There's a number of systems that are out there designed for LEDs. I'll show you one of them that we tested out. LEDs can be tuned to different wavelength features. So we have an LED that's mainly focused around 255, but has kind of a broad shoulder here. We have a 265 LED. We have a 282 LED, which obviously extends down to say 270 up to say 290 in this half maximum. So all these LEDs I'll be talking about in a little bit are really effective for disinfection as well. And then we also have the krypton chloride excimer lamp, which is a new technology we've been working with quite a bit that emits really purely at 222 nanometers. And I'm really excited about this because this is really enhancing virus inactivation. And also this is a wavelength that is fairly safe to use around humans. It doesn't absorb deeply into skin or eyes. So you can actually use this wavelength for disinfecting air, and people can be around this UV source for much, much longer time than you can for these wavelengths, which tend to penetrate much deeper into the skin and potentially cause photo lesions to occur. But krypton chloride at 222, it's really effective for viruses, and it's fairly safe to use around people. So this is really exciting wavelength that we can talk about another time. So there's lots of UV systems out there. If you think about the scope of UV technology, these are conventional UV sources on the left, using mercury vapor lamps. So this is a typical mercury vapor lamp. I don't know if anyone uses a SteriPen. I just actually was out canoeing in the Algonquin region outside of Toronto 2 weeks ago. It was a really beautiful canoe trip. Brought my SteriPen, just took the water out of the lakes there, just put a SteriPen in there, 30 to 90 seconds, and disinfected the water, drank it the whole time, didn't get sick. It's great technology. I really love bringing it places, especially when you travel internationally as well. This is a low pressure mercury lamp. It works really fast and there's no chemicals at all, and it disinfects your water. You can have small systems like this, this household-based system, maybe like 3 to 5 gallons per minute. You can disinfect your toothbrushes even. You have these UV robots that can go into rooms to disinfect surfaces. They use these a lot in the hospitals. These are all conventional technology. On the right-hand side, we have LED-based technology, and this is an example of a type of LED, basically a small chip here. And we've got lots of technologies that can be kind of generated out of this LED technology base. There's even like a water bottle. This Camelback has LEDs in the in the cap. There's the Pearl Micro, which is a technology developed by Aquasense, and this could be like in a refrigerator in your water line. It could be in a water cooler. There's these caps that you can have for your water bottles. I'll talk about this Pearl Aqua system. This is the LED system we've been using for our disinfection studies. So lots of opportunities for UV. There's just, you know, tip of the iceberg kind of applications. There's way more that you can imagine as well. So what are the benefits of UV? I mean, for LEDs, thinking about these small chips, I mean, these are really small millimeter sized UV emitters. I mean, if we can get these distributed, we can put them all over the place and have disinfection. Really think about distributing LEDs, you know, around in pipe networks or for water protection of water sources, but certainly increasing the end user in this case, you know, whether it's on your faucet or under your sink or, you know, in your water bottle. It's definitely part of a multiple barrier microbial defense. It can control all types of microbes with a very low dose. So very quickly, just a matter of seconds. You saw with the SteriPen, it takes 40 to 90 seconds, but typically most UV systems act in less than 1 to 5 seconds for disinfection, which is kind of incredible when you think about chlorination requires, you know, 20 to 40 minutes, maybe 60 minutes, depending upon the dose and the CT value that you're required to achieve. UV acts in just a matter of seconds, and it limits DBPs because there's no chlorine, there's no halogens, there's no halogenated byproducts. So yeah, no problem with DBPs at all. You can easily integrate them into, you know, into infrastructure. You know, if you can think about putting them on the end of a system, maybe in the middle of a system in a piped, in a couple that brings two pipes together, you know, there's no chemicals, and it's really ideal, I think, for small systems where you have a lot of point of use and point of application collection, and that you can also automate UV systems. There's no chemicals to use. There's no extra supplies to bring. You know, you can it's all electrical signals. You can you know, monitor this through a cell phone. So I think there's a lot of great benefits of UV applications. So let me quickly walk you through some of the vision that we had in different aspects of UV applications outside of the treatment plant, and then talk about some small systems as well in the study we did. So again, thinking about this whole kind of ecosystem outside of the water plant, you know, we think about at the water plant itself, we know that UV works. It's used as a primary disinfectant. I mean, it's used in the largest water system in the world. You know, New York City, where I'm from, I grew up in Manhattan. I'm proud to say that New York has the largest, treating about 2 billion gallons of water every day using UV light, and that's to protect against cryptosporidium mostly. It's got high levels of protozoa activation, which is great because chlorination doesn't work at all for cryptosporidium, and it's very poor for Giardia. But UV works as fast as it does for anything else. It's really well researched, validated, no problems there. It's used all over the world. It doesn't have a disinfection residual, which is sometimes people say that's a concern, but in some cases, maybe that's a benefit, because in a lot of places, maybe you don't want to have that taste and odor issue, or those DBPs. But certainly for treatment plant-based applications, it's well accepted. Getting outside the plant's not as much used. Certainly thinking about UV in a transmission main, this is a picture of a UV system just in line in a water plant. You can think there's water mains like this all over the place, buried in cities all over the world. You can think about UV applications, you know, as a booster, maybe application throughout a distribution system. But certainly outside of the treatment plant, you can think about UV applications, small and large, in pipe mains. It could be at the entry to a distribution system. It could be at the distal end. You can get high inactivation very quickly. This water's, you know, cruising through here at, you know, 20, 30 million gallons per day. You know, just a few seconds, if anything, of contact time. This isn't really implemented as far as outside the treatment plant, though, but it's certainly an opportunity that's an easy one to implement. in storage tanks. If you've ever been to New York, there's storage tanks all over New York City on top of buildings. I always wonder, where's that water go? Is that used in the buildings that they're serving? Is it just pressure? Is it fire? Whatever it might be, there's certainly storage tanks all over, but these are often ignored, and these can be breeding grounds for microbial growth, for biofilms. Having UV in here, there's lots of different ways you can think about adding UV. It could be, some floating ball, for instance, that's bobbing around in there. It could be on the lights on top of the ceiling in the system, but these aren't really used yet. And we don't know something. We just do some research on this. We don't really know the implications on the materials and if it's really going to control biofilms. Can you pulse it on and off? Do you have to have it on all the time? Is it, is it going to disinfect pathogens? Will it have any impact on water quality? These are questions we need to ask and things research we need to do. But certainly there's good opportunity to add UV in these kinds of situations where, you can add some disinfection as the water is being stored. The point of entry or point of use, UV is already used, in a lot of these cases. It's well established as a primary disinfection for like water coming out of a tap or water going to a building. Small systems are available, already validated by National Sanitation Foundation. These systems are validated by different organizations as well. This can be an easy way to provide disinfected water on tap, on demand. There's no taste or odor issues if a lot of people are averse to chlorine taste and odors if you're not used to that. And then certainly in building systems, it could be helpful for controlling issues around sloughing of organisms, Legionella, those kinds of things. Then getting out to the distribution system, this is where it gets a little bit far out, but I really think there's opportunities here. Is there a way to maybe control biofilms if we had UV throughout the distribution system, these LEDs kind of embedded into pipe systems? Is there a way to think about adding types of disinfection in these areas of the distribution system? With LEDs, I think there are. Other things you might think about are these little UV robots that might go through a pipe network, and have a bunch of LEDs on the outside, just kind of rolling through the distribution system, disinfecting the biofilms, disinfecting the organisms as it cruises through. Could be part of a cleaning process, could be part of a upkeep process. But there's ways to think about, given the LED technology, how we can implement UV, all throughout the water distribution network. But more questions to ask, of course. What are the pipe materials? Are they going to degrade? We're really controlling biofilms. Are we controlling opportunistic pathogens? Are we changing the water microbiome even, in ways that we didn't anticipate that might either offer the opportunity for better control of pathogens, or maybe there's even some type of probiotic effect of UV compared to chlorine. We just don't know. And then, of course, we have to power these sources. And the nice thing about UV LEDs is they can be powered directly by DC current using solar and other renewables. So there's a possibility there. And we have to think about how to marry the solar opportunities with some of the LED disinfection opportunities. So that's kind of our far out vision for how we might integrate UV further outside of the treatment plant. But more practical application is certainly, how are we going to think about adding UV to the more vulnerable water systems? And we asked this question. It was one of these things that, as a researcher, you really kind of reverse. You never really want to are we going to do a year-long study? It's going to take forever. What if this doesn't work out? But we just decided to do this study as part of the DRISC Center. We had a small systems center at Boulder a couple of years ago. One of my former PhD students, Natalie Hull, who's a professor at the Ohio State University now, she worked with the folks up in Jamestown, which is a small town, about 300 people, just outside of Boulder, about 20 minutes up the hill. They get water from a really nice clean creek throughout the year. And they agreed to let us put in a UV LED system and leave it there for a year. And right in parallel with their chlorination system, they use slow sand filtration as their primary treatment, and then they use chlorine. And we said, well, let us do a side-by-side chlorine challenge with chlorine versus UV, throughout the year, have this battle going on for the whole year. So we can easily get up there and test it. We went up there every couple of weeks and took measurements. But as far as small systems go, these LEDs have a really small footprint. They're really, resilient systems. You can intermittently operate LEDs that you can, monitor them autonomously. no mercury, no residuals to deal with, minimized DBPs, low power, and it's compatible with photovoltaics. It seems like a no-brainer, but no one's ever did a really long-term study. So we went ahead and tried this out. We used this system called the AquaSense, the Pearl Aqua. Now it's called the Pearl Aqua Deca, I think. But this has 282 nanometer LEDs, and this is what the peak output looked like. Wavelengths between about 270 up to 290 are emitted through this system. And we just took a small side stream off of here, about 0.5 liter per minute, the system, and we ran it through this Pearl Aqua, and we set it up, and we monitored it throughout the year. And we did this side-by-side trial against the chlorination system. So this data set shows the water quality data from January throughout the whole year that we ran the study in 2017. And the data I'm showing here are turbidity in purple. So the turbidity went from about 0, around 0.1 or so, up to about 2 NTU throughout the year. And you see that during spring runoff, you start getting in May and June, and in the summertime we get this turbidity peak. And then as far as water temperature goes, water temperature is very, very cold in the winter, obviously. And then as summer comes up, it gets up to 15 or so degrees and comes back down. And then the UV transmittance is up here. There's pretty good UV transmittance, about 95% or so, which is really good. But it dipped down to under 80 to 85% during the spring runoff, when you have lots of particulates and organics coming off, and then it kind of goes back over the year. So we really dealt with this varying water quality, and the LED system, we didn't touch it for the whole year. All we did is collect samples. We didn't clean it. We didn't replace it. We didn't check the bulbs and nothing. We just let it run. We knew it was on. We saw the signal, but we didn't touch it. We just wanted to run and see how it would do throughout the year. And looking at the microbial water quality coming off this, we measured ATP kind of as a measure of microbial activity. We measured total coliform. We measured E. coli. And the data here show the filter effluent, which is FI, filter effluent. This is in and out of the slow sand filter. And then we have the chlorine treated water and the UV treated water. So looking here, for instance, in total coliform, coming in the filter influent, we saw coliform kind of varying up to 300 CFU per mil. Here and there, we saw a little bit coming out. Even the filter effluent was pretty good for coliform, but we basically saw 0 hits for the chlorine system and the UV system. They both performed really well. As far as coliform goes, the same for E. coli. We saw a little bit more E. coli coming off of the filter effluent here in orange, yellow, but out of the UV system, out of the chlorine system, we actually saw 0 E. coli the whole time. When we look at ATP, these are really interesting results and something to do that you might think about, but we saw the microbial activity from the ATP. We saw some numbers, and even out of the UV system, we see ATP signal, which is really interesting, but it really stems from the fact that, UV doesn't actually destroy the bacteria like a chlorine. When it attacks the bacteria, it will destroy the membrane, kind of break it apart, spill its guts. UV doesn't do that. UV just destroys the organism's nucleic acids, but it actually still can respire. It's still somewhat viable at that point. It can't cause an infection, but it's still technically alive until it dies off because it can't reproduce. So you do see that ATP signal, which is really interesting. We're trying to look more at this ATP as an interesting indicator for UV applications, but certainly coliform, E. coli, didn't see any at all throughout the whole year, which is pretty incredible, both for the UV and the chlorine side. So at the end of this demonstration, this UV LSE reactor, it's resilient for a year-long application. It went through adverse conditions. We had no maintenance at all, as mentioned, near freezing temperatures. We had spring runoff issues. As far as the town was concerned, they're really excited about it. The whole system for the whole year, it cost less than $25 to run. This is, again, just a 0.5 liter per minute. And these are actually systems that are now, I'd say, 10 times more efficient in today's kind of time in 2022 versus in 2017. There's great improvements. We'd see even lower costs now and easily higher flow rates and higher doses. But these are doses for around 40 millijoules per square centimeter, which is a typical dose that you want to see for disinfection. So we're really excited that we maintained the disinfection performance with no chlorine added and operated as good as a chlorination system for all the indicators we were looking at. And we put a paper out in AWA Water Science, and this actually won the best paper award for the small systems division. So we're really proud of this work. Really good to invest the year, and will herald undergrad who helped out tons on this, but Natalie did an amazing job with this research, and we're really excited to finally have a year-long trial that really proved that UV LEDs can work. So thinking about applying this, around the world, we're really excited about UV technology. It's definitely something we feel like needs to get out and protect public health all over the place. And we do a lot of work in countries, low and middle income countries, that have concerns with water quality around their hand pumps, community piped water systems. There's no reason why we couldn't put UV in these systems. We need to sustain services in these communities, need to protect water quality. Oftentimes you bring chlorine in as a solution, and if folks aren't used to chlorine, or they don't like to put a chemical in their water, for instance, maybe they think about water a lot differently than people in North America do. It's not just an object that we're consuming, it's actually part of the spiritual world, and it's part of the, the earth. Why do you want to put a poisonous chemical in it? That's kind of baffling a lot of people, and so I think we need to be considerate of those types of cultural concerns. And just practically, the taste and odor of chlorine, people don't like it often. So if you can come up with a solution that's not going to change the taste and odor, maybe there's ways to think about integrating UV into tap stands. So when folks come and bring their jerry cans or to a hand pump, is there a way to challenge yourselves? So can we integrate an LED disinfection system in this network, in this pipe, in this hand pump? Can we power that as the hand pump is going up and down? Can that power the LED system? Can we get a small solar system on there to help power it? There's lots of really interesting applications and research we need to do to bring safer water to these communities. So, in the end, I really want to think about the magic. UV is magic to me. I mean, it's like you can't smell it, you can't see it, it just happens. I mean, it's light. It's pretty incredible. But is there a way we can think about UV, bring it to more places? And certainly proven technology for disinfection. We know that in point of use and point of entry, no reason why we shouldn't use it immediately in any place we can, because it's going to protect public health and disinfect pathogens. Systems that don't use residuals. I mean, if systems, like say in a small distribution system in a small rural community, not required to have a residual, there's no harm in putting UV in. I mean, it's going to help that system and help meet compliance and microbial issues. I think, as we think about infrastructure reinvestment, it's the talk of the town, obviously now in the U.S. with the various bills out of the government, but the pipe replacement that's going to have to happen with lead pipes and corroded pipes and ancient infrastructure almost in a lot of communities. Can we install new systems that have a thought to the future, maybe embedding UV, at least putting UV in along the distribution network? Thinking about that now, and as we build those systems out, make sure we have room for new applications. And really, for small systems, it's almost a no-brainer. It's an ideal solution. We definitely need innovation among the engineers, to integrate UV into hand pumps and tap stands, and really bringing the technology to really to bring it to people, make sure they don't even notice it's there. They shouldn't even know it's there. They don't need to know it's there. All they need to know is that the water that's coming out of that hand pump or that a tap stand is going to be safe and free of microbial contaminants. So I want to recognize Natalie and Vanessa, who helped develop this vision of kind of UV outside the treatment plant, and obviously Natalie and Will for this great research that we did in the small system just outside of Boulder. And I thank you all for your attention. Again, thank Fulbright Canada for helping me get to Canada, where I have so many great colleagues and former students and hopefully future collaborators. So thanks, everybody. Happy to take your questions.
Oh, that's fantastic, Karl. Thanks for this awesome presentation showing this vision. We do have a